there are a lot of different types of exponential growth. The simplest of which is what we call uninhibited growth, which basically over time will continue to grow, not at the same rate, but at a consistently growing rate. Again, as we discussed before when we were talking about interest, there's a difference between linear and exponential growth. Linear growth is a straight line growth, which has a consistent slope over time. It will, rise or run. It will grow by the same amount year by year by year, or whatever the x-axis is. Exponential growth, however, grows more and more over time, has that curvature that we see with exponential functions, and it's the basic shape of uninhibited growth. Now, if we look a little bit about the excerpt from our text, it says the equation dp dt is equal to kp, or p prime is equal to kp. What this is saying is that the derivative of the function should be equal to a number k times the original function itself, which it kind of goes on to explain what that means, but I'll try to put it in my own words. Basically, uninhibited growth should grow. The derivative gives you the growth rate of the function itself. And what it's saying is that the rate of growth should be equal to the original size of the population times k, where k would be the growth rate, or essentially saying if p represents a population of people, for example, the more people that you have, basically the larger p of t would be, we'd expect the growth rate to be larger as well. And there's a reason that a lot of natural populations undergo uninhibited population growth without some form of an inhibitor. Now, uninhibited growth is unrealistic, and we'll get to why with a couple examples. But usually populations undergo uninhibited growth for the original growth period. And again, just as a way of explaining why this occurs, basically the more people you have, the faster it will grow, because there's more people to reproduce. And k is just a constant multiplier, which could be 2, 4, 0.3. Usually it's like a rate percentage, like 0.05 or something, which describes the rate of growth of the population. And basically the speed of growth will increase as the population increases, which is very common for growth, how things grow in nature, like bacteria, money, human growth, etc. But let's look at so it also goes on to say, well, what is the solution to such a, what we often call this a differential equation, an equation which has not only a function but its derivative and is involved. This is one of the simplest differential equations there is, and there's an entire course and multiple courses centered on solving different, more convoluted types of differential equations. Very important for physics, engineering, and so forth. Anyways, but what it says is that the only function that satisfies this equation, basically, or in other words, the only way you can properly produce such a function which has a proportional growth rate to its original population is if it is an exponential function base e of the form c e to the kt, where k is the growth rate, c is going to be your starting value of your population, as we've seen, and t is going to be the time frame. And so to look at why this is, let's go ahead and look at, well, here's f of x equal e to the 4x, and I'm just picked a random number to be k, and then it asks us, well, what is f prime? And as we know, to take the derivative, well, we know our baseline derivative, the derivative of e to the x is just e to the x. It's the only function which has its own derivative, or is its own derivative. But, when we insert something else into the exponent, again, f prime is always equal to, well, what's the derivative of my function e to the 4x here? Well, here I know the derivative is e to the x, of e to the x, but here we have a 4. And so what we always have to remember in such instances is, well, what about the chain rule? I can take the derivative of the outside, so the derivative of e to whatever is e to whatever. It's the same thing, keep the exponent the same. However, whenever there is anything other than x in there, the chain rule has to be applied, because I could think of this as e raised to a function. The derivative of a function within a function is take the derivative of the outside, keep the inside the same, and then multiply by the derivative of the inside. So the derivative of 4x is just 4. So at the end of the day, what I should have here is a 4 popping out, or 4e to the 4x, as the derivative of f of x. And well, notice that this function, the derivative function, which gives us the slope of the original function, is almost exactly the same. The only difference is there's another 4 here. And we can see why this potential solution, e to the kx, makes sense for proportional growth, because its derivative will have this proportion, this constant multiplier that comes out front. And that gives us our scaling factor for the growth rate. And obviously, populations usually would not have values of 4, because that implies that the growth rate is 4 times the size of the population. And again, I could rewrite this as f prime of x is equal to 4 times f of x. And again, it kind of suffices in this uninhibited differential equation. Or again, I could even write it using Leibniz notation. df dx is equal to 4 f of x, or just 4f if you prefer. But we can see it has that that same structure. And it's describing uninhibited growth, which again is proportional to the original. And typically, that number is not 4. Anyways, let's look at an example. The example below says, in 1971, Intel Corporation released the Intel 4004 microprocessor, which held 2,300 transistors. Since then, the number of transistors on a microprocessor has been growing exponentially at a rate of 34% per year. And if that trend continues, if it continues undergoing uninhibited exponential growth, how many transistors will be on a microprocessor today, and find the doubling time. So basically, the amount of things we can fit on a processor has increased exponentially over the course of the last 40 or so years, or 50 years rather. And again, this growth rate or percentage was determined it wasn't based off data today, but again, we could go ahead and use it as a projective model. If it has undergone the same uninhibited growth, how many could we expect today? And I don't remember offhand how many microprocessors we find on, or how many transistors we find on today's microprocessors, but it is an absurd number that we can actually fit on things, which explains the power of modern computers. Anyways, let's just get right to it. So also another kind of summary about all of this, the important thing I'm trying to get across is that when we see things that are growing exponentially, usually E is going to be a proper model. And the model for such would be, well, what's the initial population times E to the growth rate times T? And this is where you can begin. Now, sometimes you use other bases than E, but it is the only solution which undergoes and exhibits proportional growth, which is usually what makes the most sense. Now, especially with natural populations. With this example, it might not necessarily make sense that it would need to be proportional. So, but you can always start with that model, because as we talked about with compounding and E, the relationship is pretty similar. The sort of predictive model numbers are pretty close, whether you use E or whether you use other things to fit the data. Anyways, let's just get to it. So again, our future value of microprocessors at time t will be equal to the initial. Well, so we were told that in 1971, that's kind of our frame of reference. There were 2,300 microprocessors on the transistors, and the growth rate is going to be our k, which is 34%. Oops, not 0.034, 0.34 times t. So this function should model our the future value of microprocessors over time, assuming it is undergoing uninhibited growth. And notice it's not specific, but just because it says it's growing exponentially, this would be a fine assumption. So we could say, well, what about today, or even let's just say in the year 2000. So since 1971 is going to represent the 0, remember that the 0 value here will produce e to the 0 power, which is 1. So 2300, that starting value should always correspond to the domain input of 0. So what I could kind of remember is that for 1971, t is equal to 0. And so, let's say I wanted to know in 2000, that would imply that's 29 years later. So I want to know, well, what's f of 29 to find the year 2000? Or say I wanted to do 2021, that would be 50 years in the future. And so I would want to check f of 50. So f of 29 would just be 2300 multiplied by e to the 0.34 times 29. And obviously gonna want a calculator to do this. That's pretty close to a third, so I might be able to approximate what that would be without it, but let's just type it all in. Would give us a very large number, which is looks to be about 44 million. 44 million. And again, I can round because this is just a projection. This is not a perfect estimation, so often we would want to round it to 2 or 3 sig figs anyways for a sensible answer. But that's a whole heck of a lot. And actually, if you Google how many transistors are on a microprocessor and look at kind of a time-lapse graph, it's very, very interesting model, and it does exhibit exponential trend mostly. And you'll see that the number of transistors is mind-bogglingly large. And so same thing for 50. I would just want to replace the 29 with 50 in my formula. And this would give me an even insanely larger number. As we talked about with exponential functions, they grow at a really they'll grow faster and faster and faster because the more and more, like again, taking it back to human populations, the more people you have, the more people you have to reproduce. And the speed at which it grows, and this is a big problem the Earth faces, having over 8 billion people, is that we're constantly growing. We have more and more people. Overpopulation is going to only get worse and worse unless there's some other inhibiting factor. And I do want to talk about inhibited growth in another video. But anyways, this comes out to also, I don't know if I've mentioned this to you guys before in this class, but if your calculator reaches basically the numbers are too large to display, it will use scientific notation in the form of this little e. So this e, you can remember, means multiply by 10 to the 10th power, or move the decimal 10 places. So basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Since billions place is 9 over, this would actually be about 56 billion microprocessors on this transistor. And we can check for the accuracy of this figure by Googling how many transistors are on a microprocessor and just see what we can come up with. Transistor count, and if we look at the graph, actually it looks more linear upon first inspection, but if you are looking at the scale of the graph, it's actually not in a linear scale. And this is often what we call an exponential graph, where it's using powers to describe the scale of those numbers. And notice that in 2020, the number of transistors on a microprocessor is in the range of about 50 billion, which is remarkably on point with this exponential growth function. Anyways, in the next video, we'll talk a little bit more about inhibited growth models and a few other applications of uninhibited growth and decay.